All right, so we're going to talk about how the internet works. Briefly on me, my name is Jessica McKellar. I'm a director for the Python Software Foundation. I'm also an organizer for Boston Python, which happens to be the largest Python user group in the world. We actually just crossed 4,000 members, so that's very cool. I'm an open source enthusiast. I do a lot of programming community outreach. I'm a maintainer for the Twisted asynchronous networking framework in Python and a variety of other projects. So, a little bit about me. Okay, but how the internet works. This is the question that is nominally the point of this talk. Although I have to admit that the real point of this talk is for me to share my enthusiasm for networking with you all. Okay, but this is the question we're nominally trying to answer. You type http://python.org into your browser bar and you press enter. What happens at a networking level to get the python.org homepage displayed on your screen? And I'll argue that this is at least 4 different questions. So one question is, what is python.org? Like, conceptually, physically, what is python.org? Another question is, where is python.org? Out there in the universe, where is it? How does my computer talk to python.org? And once they're talking, what does my computer actually say? So let's try to answer each of these questions in turn. While we're having this discussion, we're going to talk about a lot of specific networking protocols. And a protocol is just a format and rules for exchanging information. That's all that is. When we're dealing with the internet, protocols are layered. So they work together, one protocol per task, to get useful work done. OK, so our first question was, what is python.org? And really, python.org is a host name. It's a nice, convenient, human-readable, memorable representation for an underlying service. So it's a human-readable identifier that maps to an underlying unique numerical identifier, or IP address, that distinguishes a particular host out on the internet. So an important part of answering this broader question is going to be, well, how do we go from a host name, which is what humans like to talk about and can remember, to an IP address, a unique numerical representation out on the internet that computers can use to talk to each other. Unfortunately, there's a protocol exactly for this. That is DNS, the Domain Name Service, and its whole job is to translate host names to IP addresses. So for example, python.org, that host name maps to 82.94.164.162. So what literally happens every time you go to visit a new website out on the internet, before you're talking to that website at all, there's a prerequisite step. And that step is looking up the corresponding IP address for that host name. So when I pull up Firefox and I type in python.org, the very first thing that happens is my computer makes a request to a DNS resolver saying, hey, what IP address is python.org? The DNS resolver spits back a response, and I use that IP address for subsequent communications about that host name. OK, so step number 1, done. Step number 2, where is python.org? Well, fortunately, we have a protocol answering this question as well. This is the Internet Protocol. IP's job is to handle addressing and routing throughout the internet, and that IP and IP address is this IP. So I don't have a direct line to python.org. I have to use the internet, and my packets are going, my packets of data are going to hop through several intermediate computers on the internet, or routers, to get from point A to point B. So a really important question here is, well, who figures out what the right path to take is? And that's IP's job. And the best way to learn more about this is really just to do it interactively. And fortunately, Python has some really good tools for doing this. One of them is called Scapy. And Scapy will let you interactively, at a REPL, experiment with networking stuff. One of the things that it will let you do is it has a built-in traceroute function that will do some work under the hood to tell you, for a given host name, what the hops through the internet are to get from your machine to that destination. So I ran that command, and it spits out a bunch of data that was really fast. So why don't we sort of zoom in on the important parts? And I've added a little bit of metadata here. So at the very top is me. I ran this on my laptop at home. I live in Boston, Massachusetts, in the US. At the bottom is the information for python.org. And the left is IP addresses. And on the right is the host names. So that exact DNS mapping host names to IP addresses, we're seeing that encapsulated line by line in this traceroute output as well. And so we see it takes quite a bit of effort to get from point A to point B. And there's a little bit of a hint if you look at the host names about maybe the path through the internet that my packets are taking. So this is interesting, 15 hops just to get from my computer to python.org. And we can get even more information about this. One of the nice things that Scapy will let you do is that you can generate a graph for the metadata about this trace route. So why don't we go ahead and do that? And here's the zoomed out version of the graph. Again, there's me at the top, and there's python.org at the bottom. And what we're seeing here are a bunch of colored circles. Each circle represents a router, one of the hops through the internet. And each color represents a different internet service provider or company who's managing the underlying physical hardware, the routers that make up the internet. So we see here a lot of steps, a lot of different companies who are working together to allow my traffic to get from point A to point B. And we can drill down on this a little bit. So from the US, a really popular ISP, not that we have a lot of choice in the US, is Comcast. I start out going through Comcast, we go through Cogent, some hops through IS, then we eventually get to python.org. And one of the things that's cool about seeing it in this graphical representation is a reminder that a lot of competing entities are working together cooperatively so that I can browse the web for cat pictures. I mean, there's a lot of politicking going on to make this work under the hood for us day to day. So I think that's pretty cool. But there's even more that we can do with those traceroute IP addresses. One thing we could do is we could use a geolocation service to figure out their approximate physical locations for the routers that correspond to these IP addresses. So why don't we go ahead and do that? There are a lot of free and commercial services that will do this for you. I picked one that has a really simple Python API. And so what I did is, given those traceroute IPs for each one of them, do a geolocation lookup and print out some of the basic location information. And I don't know if any of you have a guess for where python.org might live in the world, but if we do this work, we find out that python.org actually lives, the physical hardware for python.org actually lives in Amsterdam. So every time that I want to go to python.org and request information, data from Boston has to make a pretty serious trip all the way from Boston to New York. This is via physical cables in the ground or above ground. From Boston to New York, somehow crosses the Atlantic to London, and then to Amsterdam, and then back again so that I can get the response from the server. So that's pretty amazing as well. And it's worth dwelling on this transatlantic trip for a moment, because, I mean, if you think about it, some company laid giant cables under the Atlantic Ocean, and they're, shark-proof, terrorism-proof, whatever. It takes a lot of engineering effort to make this happen. And this is part of what is so interesting to me about networking is, again, it's the complicated series of software and hardware and political engineering that goes into this just working most of the time. Okay. So that was sort of a roundabout explanation, but we now know pretty concretely where python.org is. We know that there's a server somewhere in Amsterdam that is serving responses to my requests. And the sort of the workhorse protocol for this is the IP. Well, the internet protocol, not IP protocol. Be redundant. Okay. So question number 3. How does my computer talk to python.org? There's a protocol for that as well. The Transmission Control Protocol, or TCP, allows us to reliably deliver data from point A to point B. I say reliably, why does that matter? Well, in general, when you're talking between two servers on the internet, things just work. Packets get from point A to point B. It's maybe a complicated series of hops, but it does basically work. But occasionally things go wrong. One thing that could go wrong is that a router on the internet could get really backed up. It could be servicing a lot, it could be handling a lot of packets, and it gets full. And it gets so full that it says, I can't handle any more packets, I'm going to drop any new packets that I receive on the ground. So that's one way that packets can get lost. They can get corrupted. If you sit next to a really strong microwave, it's possible that bits get flipped in your packets that cause them to not successfully reach their destination. So there are a variety of things that can cause your packets to not get to their intended destination. And we need some way of compensating for that. So TCP does this. TCP will take care of retransmitting lost or corrupted data. And so the two ends of the connection are keeping track of what data has successfully been sent and received, and they'll handle retransmissions through keeping track of that extra information. And as it turns out, this idea of a reliable transport is a pretty good idea. So most of the internet work that we do uses TCP as an underlying transport mechanism. So when you browse the web, if you're using a chat service, if you're checking your mail, all of these application layer protocols are using TCP under the hood as a reliable transport mechanism. Which makes us have to think about, this sort of poses a question for us, which is, if I have a single server, like there's an IP address representing hardware out on the internet, and I want that server to have multiple services, like maybe I want it to be a web server, but also a way to check your mail and also a chat client. Well, all of these things use TCP, and they're all dealing with the same IP address. So we need some way of disambiguating the TCP streams for these multiple different applications. So the way that we do that is we give a port number, just a port, which is just a number, to each application. And then your networking stack in your operating system can use that port number to disambiguate the different streams of traffic. So ports are an important idea when you want to be able to multiplex different applications on a single transport mechanism. OK, so how does my computer talk to Python.org? It talks reliably using TCP. So that brings us to question number 4. What does my computer say to Python.org? So once we've established that reliable connection, what is the actual communication? And this one is probably familiar to all of us. When we're browsing the web, we're using the Hypertext Transfer Protocol, or HTTP. And we use HTTP to request resources from servers. And so in fact, when you type in the http://python.org, or these days your browser may do it for you, that HTTP is important. It is specifying the application layer protocol you intend to use. And what do I mean by resource? Well, a resource can really be anything, but often it is an HTML web page, it's an image, it is textual or binary data, or maybe it's data generated on the fly if you're querying an API, or if I visit whattimeisit.com, that is dynamically generated content that I'm receiving. One of the really cool things about HTTP is that it's a textual, human-readable, pretty simple, line-delimited protocol. And that means it's actually really easy for us to pretend to be our own web clients. I mean, there are a lot of ways that we could do this, but one tool that most of us have installed on our machines right now is called Telnet. So why don't we pretend to be our own web browser? So we use Telnet. We say we want to connect to a particular host on port 80. 80 is the port for HTTP. We establish a connection, and then we issue an HTTP GET request for /, which is the root resource, the home page for python.org. Complete the rest of the protocol dance. And then we get back a response, which is, in fact, an HTML web page. And that flew by pretty quickly, so let's drill down on the important parts. So one thing to notice is, when we're making that connection, what is the very first thing that has to happen? Well, we have to map that host name to an IP address, right? So we have that transparently under the hood. Before we do anything, we do that DNS lookup, so we get the IP address that we can use to establish that reliable TCP transport. Once we've established that connection, we can now issue the application layer requests. So in this case, the HTTP request. And when we get a response, we get a couple of things back. So first, we get back a status code. In this case, it says, OK, 200, OK. Everything was good. I understood the request, and I was able to service it. Sometimes things can go wrong. If you've ever gotten a 404, a 500, things can go wrong when you query for resources. We also have some headers, information about what the service is that's serving the request, some date information, the content type. In this case, it is in fact an HTML web page. And then we have the data itself. And if you've ever used, in Python, a library like URLlib or requests, or Ruby has certainly analogs, and you fetch a web resource using that API, the telnet version is exactly what's going on under the hood. You're doing this DNS work, you're establishing this underlying TCP connection, and then you're issuing application layer requests. We just don't have to do all of that work ourselves when we use a higher level library. That's pretty cool. And it's no accident that the hypertext transfer protocol and the hypertext markup language share the same first two words. Their origin story is very much intertwined with the birth of the internet. Okay, so we know how to be a web client. What if we wanted to be a web server? Well, fortunately, in Python, this is really easy as well. And there are a lot of ways you could do this. My personal favorite would be to use Twisted. And this is, so Twisted, as I mentioned earlier, is an asynchronous networking framework in Python. And this is a twisted HTTP echo server, or it's 95% of it. All it's missing is the imports, actually. And you could, so if you had the imports, you could copy this file and run it on a server out on the internet. And then other people on the internet could, in fact, connect to and request resources from this service. So this is all it takes to be a web server, which is pretty cool. And what are the important parts of this? Well, okay, we're implementing a class that implements the HTTP protocol. We receive lines, and we respond to them. The very first thing that we issue in our response is that 200 OK status code. Towards the bottom, we see that the first thing that we do is we establish a TCP connection on port 80. It's all coming together. So TCP connection on port 80, and then the final line, the reactor.run, just says to do it forever. I want you to listen for requests and respond to them forever. And this is the important bit of what a web server does. So whenever you visit Google or Wikipedia or whatever, and Apache is running under the hood, this is like the important part of what a web server is. And I think it's very cool that you can fit all of this on a single slide. Like conceptually, the important bit is right here on one slide. That's cool. Okay. So now we know, quite concretely, through experience from the client side and from the server side, what my computer says to python.org. We use the HTTP protocol to request resources from servers. Okay, we only had 4 questions. We've answered all 4 of them. So now we really have a good answer to what happens when you type this into your browser bar and press enter. So we know that the very first thing that happens is we use DNS to resolve host names to IP addresses. Once you have that IP address, you can now handle the addressing and routing question for how to get from point A to point B. You can establish a reliable TCP connection, and over that connection, you issue application layer requests, in the case of making web requests using HTTP. A really fun way of exploring this stuff further is using a utility like Wireshark. And what Wireshark lets you do is, when you run Wireshark, you tell your computer, hey computer, I want you to listen really carefully for any network traffic that you can hear. Even if it's not for me, if you can hear it at all, I want to know about it. And display it all to me in real time. So sort of be a little bit nosy and listen to everything you can hear. And so you'd be surprised how many Saturday mornings I spend with a cup of coffee doing this at home. And here's an example of me turning on Wireshark, saying, computer, hey, listen, and then catching some traffic. When I was doing this, it was just me at home by myself with a couple of servers, and in just a couple of minutes, it was you generate tens of thousands of packets. So a ton of stuff is going on under the hood. So we see tons and tons of traffic for a variety of protocols flying by. Why don't we drill down on some of the interesting stuff? So one thing that we see is surfing the web. And it's exactly the way that we walked through it earlier. We see that the first thing that happens is a DNS lookup. In this case, I was visiting the Boston Python homepage. So we do a DNS lookup for bostonpython.com. We establish an underlying TCP transport, and then we issue the HTTP request, a GET request for the homepage. So I wasn't lying to you. This is exactly what actually happens. interesting things that you see? Well, one thing I saw is that I have a printer, and that printer is networked, and it's really lonely. It, without anybody asking, it periodically issues requests saying, hey, I'm a printer. Would anybody like to print to me? I would really love it if someone would like to print to me. So lonely printers. We also have lonely TiVos. The TiVo would like someone to play with it as well. Probably lonely Xbox, too. We have an Xbox. So these devices should all get together while I'm not home, clearly, because they're pretty bored. Another thing that you see is errors. So we talked about packets getting corrupted or dropped. I mean, I was seeing this even at home. TCP retransmitting packets because errors had caused them to not get received by the destination. So TCP doing its job even at home. Another thing you can see is encrypted communication. In particular, that the handshake, the setup work to establish an underlying encrypted channel so that snoopers like me cannot see our communication. So you can see all of the steps of the handshake in Wireshark. Speaking of encrypted communication, who here uses IRC? Maybe even right now? Yeah? Okay, cool, yeah. Guess what's not encrypted? IRC. So in fact, I could, with Wireshark on, I could watch myself go through all of the steps of giving my credentials to an IRC server to log into it. So, for example, here is me connecting to Freenode, the service prompting me for my password, and me responding with my password, Django for life. So, it's just something for you all to keep in mind as you're here today with me on IRC. Okay, so Wireshark. It's a fun tool for interactively exploring networking. I have one final example, which is fairly gratuitous, but it's just very fun, so I wanted to share it with you. So the setup for this is, if you remember our lonely printers from a couple of slides ago, there's a protocol here that we haven't talked about before. And that protocol is ARP. This is the Address Resolution Protocol. ARP's whole deal is that it maps hardware addresses to IP addresses. And when I say hardware, what I mean is, in this laptop, there's a network card, or possibly several network cards. There's hardware responsible for sending out the zeros and ones that make up our networking transmissions. And this is something that operates at a lower layer than IP. So an IP address maps a host name to sort of a computer, but a hardware address or a MAC address identifies sort of the individual piece of hardware responsible for the networking transmission. And so there's a protocol just for this, the ARP protocol. And in particular, so you use ARP to figure out who else is on your local network. So me and my TiVo and my printer would all be using ARP to figure out who each other is. The most important part of ARP, or the most important application of ARP, is that you use it to identify your gateway router. By gateway router, I mean when I want to do stuff on the internet, all of the traffic that I generate has to go out through an actual machine, a gateway router, that mediates between the local network and the broader internet. So the gateway router is really important because it is sort of your access point to the internet. And the funny thing about ARP is that it's trust-based. So if you wanted to pretend that you were someone you were not, if you wanted to pretend that you were the gateway router, you could, and other computers would listen. There's no authentication there. So let's see how that plays out. So I'm doing a couple of things here. So the first thing I'm doing is I'm setting up a server on my local network to be able to have a web server running on it. So it's able to listen for and respond to HTTP requests. I'm also telling this server that it should be willing to respond to traffic that was destined for the gateway router. So it should snarf up and respond to those requests, even though it's not normally supposed to. And then I'm going to start up Scapy, and I'm going to craft some ARP packets that are going to assert that this server is actually the gateway server. And I'm going to send a bunch of these packets, send them, I'm the gateway, I'm the gateway, I'm the gateway. The computers on the local network are all going to believe that that's true, because that's how ARP works. And then, my hapless boyfriend is going to come home, he's doing some work, he's also a developer. He's going to look up some stuff. You're sending the packets, I'm the gateway. So he wants to, maybe he's looking up some documentation. he goes to python.org, or he thinks he's going to python.org. He tries to issue a request to python.org. My server intercepts that communication, and this is what he sees instead. There you go. Isn't networking fun? So this is interesting for a couple of reasons. One is, I mean, clearly there are some real opportunities here for you and your flatmates or partners or whatever, get creative with that. Another thing is that this is just one example of how sort of initial design decisions for networking protocols are things that we have to contend with decades later. So there are a lot of protocols are trust-based. A lot of protocols are not encrypted. And a lot of our time is spent these days worrying about the ramifications of those early design decisions. So this is a good example, and it's worth reflecting on a little bit. I will say that when I originally constructed these slides, I was not married. I now am. Aww. Well, these are, so I designed our wedding rings. This is what they actually look like. So I was not the one to propose, so I unfortunately did not get to use this tactic. But for all of the single ladies and gentlemen in the audience, I encourage you to keep this ARP poisoning tool in your back pocket in case you need it. Okay. We answered our questions. We answered our 4 questions. We answered our major question. What's next? Well, obviously this stuff is really fun. Hopefully you believe it's fun. There are a lot of really great Python and general networking utilities that are worth exploring. For Twisted in particular, if you want to learn more, I happen to have written a chapter about Twisted for a really cool book called The Architecture of Open Source Applications, Volume 2. So there are 2 of these, and if you haven't seen any of these before, I encourage you to check them out. All of the content is available for free online under a Creative Commons license, but I would encourage you to support the project as well by paying for the book because all of the proceeds go to Amnesty International. And, breaking news, the 3rd book in this series, The Performance of Open Source Applications, was just released this week. So if you want to learn about the performance of all of your favorite open source utilities, this would be a great thing to check out. So that is my pitch to you. Networking is fun. It's also something that, unfortunately, these days is very political. So the more people who have a basic understanding of how the internet works, that includes us in this room, but that includes non-technical people. The more people who have a basic understanding of the way the internet works, the more likely we are to make good decisions, good political policy decisions around the internet. So if I can leave one, piece of food for thought, it would be, what can we do as tech-savvy people, as developers, to encourage a world in which people have this basic understanding? But other than that, networking is fun. I sniff your own wireless traffic. Don't do it to others, because that's illegal. And that's all I wanted to say. So thank you. We have a couple of minutes for questions. Any questions? Yeah.
So it seems obvious that ARP is used for 2 computers on a local network to find each other. In your example where you're talking from your local network to Amsterdam, how does the packet know what route to take?
Yeah, so IP is part of that answer. The other half of that answer, which we didn't talk about because there's not time for it, it doesn't neatly fit into the stack, there's a protocol called BGP, which is happening all the time under the hood, and it's the way that networks for sort of sub-networks for particular companies, typically for your ISPs, for your autonomous systems, talk to each other to figure out globally over the internet what available paths there are. So IP gives you the information. There's this hierarchical bit of information in IP addresses, but BGP is this secret protocol happening under the hood the different internet service providers can talk to each other about what routes are available. And a funny thing about BGP is that there's a trust-based element to this as well, and there are some sort of famous examples of like oopsie-daisy BGP events. Like one example of this is one country that shall remain nameless wasn't happy with the fact that YouTube can serve content that it didn't like, and so the person who got to control BGP for the country's, there was like a state-sponsored internet service provider, and the guy in charge of the BGP for that like fat-fingered route declarations that were supposed to say, hey, YouTube, you can't route YouTube through our country, but what he fat-fingered was, nobody else can see YouTube at all. Like the whole internet cannot visit youtube.com. And this actually happened a couple of years ago, and it resulted in YouTube being down for the entire world for like 15 minutes. But the reason why that was possible is because when you use BGP to advertise routes, the rest of the internet trusts that the routes you're advertising are correct. So trust. It's great. So BGP, though, if you want to learn more about network, the sort of the behind-the-scenes networking protocols that make the internet work, BGP would be a great one to look up. Other questions? Okay. Thank you so much.